So, isomerism, this is the existence of two or more organic compounds having the same molecular formula. The same molecular formula, but different spatial arrangement in space. But if it was at the ordinary level, we say existence of two or more organic compound, have the same molecular formula but different structural formula. In that case, it's valid if and only if we are dealing with structural isomerism. But here, we don't just have structural isomerism, we also have stereoisomerism. That is isomerism of compound in space. So, in this case, our isomerism is divided into two main groups. We have structural isomerism structural isomerism normal stable isomerism. So what two main types of isomerism? Structural isomerism and stereoisomerism. Why structural isomerism? So structural isomerism now have G position functional group. Functional group. For stereoisomerism have optical geometry. So in university, you guys will see tautomerism and metamerism. So for the moment, apply the GCE program, that's what as it teach us. Chill isomerism, positional isomerism, functional group isomerism, optical isomerism, and geometric isomerism. So what I will do is that I will take an organic compound to illustrate this isomerism lesson. So consider the organic compound C4 is 10 O. You cover another one. So I will illustrate these various type of isomeric. So let's take this organic compound. So let's take chain isomerism. For chain isomerism, so I'll take 1 chain isomerism. For chain isomerism, the organic compound should have the same molecular formula, but the carbon skeleton is not the same. So consider these two organic compounds. CH3, CH2, CH2. 1, 2, 3, 4. So this is one of the isomers. I'll cut the carbon skeleton, so I'll reduce the chain. Basically, reducing the chain, I have CH3, CH2, C. 1, 2. I was supposed to put the metal document CH3, 1, 2, 3, CH3, OH. What is the physical significance of that? For chain isomerism, they have the same molecular formula, but the chain or the carbon skeleton is not the same. One can be a linear compound, the other one is a branch compound. So, let's go down to position. R2. Position isomerism. For position isomerism, they can have the same molecular formula, but the position of the functional group are not the same. In this case, the functional group is the OH group. So, see what we Upon installamos, we got CC, 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 OH, anti-tipo. Then, to have the other isomer will change the position of the OH group. I can take the OH group, I put operation 2. CSK, CH, CH, OH, CSP. These two guys are position isomers. Why? Because the first organic compound have betanes. One of have beta 1 point. The second have beta 2. Beta 2. Beta 1 or beta 2. Okay. Let's see 1 3. 1 3 is functional group isomerism. For functional isomerism, the organic compound they have the same molecular formula, but they are found in different homologous Cs. So these are the various ways atoms are isomers in ethers, aldehydes are isomers in those aromatic acids. Little acids are isomers in esters. So you have to keep this clearly in your head. Head. Sure. Range of digits. Alcohols, isomer ethers. Aldehydes, isomers ketones. Carbonic acids, isomers esters. So using that, I get you an alcoholic functional group. So I'm going to make use of the alcoholic functional group. So the alcoholic compound. So my alcoholic compound have CSC, CST, CSU, CSC, CSC, OH. That's good. For the ether one is very safe. For the ether, you would put the OH, the O group in the middle of the compound. Because the ether is R. So that the ether won't crowd. Go ahead and alcohol. Functional isomer should be an ether. So the ether should be like that. In this case, the number of carbon are 4 them. And 4 divided by 2 is 2. So in this case, I have CHKB, CH2, O, CH2, CNP. We see we have an ether. An ether on one side we have 3 carbons, the other side we have 2 carbons. How do we name the ether? There are 2 ways of naming the ether. So I'll give you the simplest one. So in this side we have an ethyl group. The other side we also have an ethyl group. So we have 2 identical ethyl groups. So we are going to say di ethyl ether. So that's it. The first nomenclature. The other nomenclature is a bit complex with ability rule. A top Z, the top Z a date. In front of one system on the education, You mostly see them many things like that. They form see a tip. The image they usually say diethyl ether. So it's good for you guys to master the two sections. Okay. I cannot just stop here by dealing for an alcohol and an ether. I have to give you also called adenine and a ketone. Even though it's not following a method, a chronology. So I'm going to give you a one adenine and ketone also. So that if you know that actually aldehydes and ketone are functional group isomers. So let's take a molecular formula C4 HKO. I have to give the aldo and the ketone functional group. So I start with aldo. Remember that aldehyde is RC double O H. Ketone is RC double O R. I have to give you aldo and the ketone formula. So the compound is a 4 carbon compound. So having CH3, 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 CH. So here's the parable. So butanol deposits on aldehydes. So for the keto one, can we CT, CHT, C double O, CH3. It's a ketone. So say 1, 2, 3, 4. Butan 2 on. Butan 2 on because the keto group separation 2. Okay. Another isomers. So let's check if actually they are isomers. So the isomer there is C 1, 2, 3, 4, C4, H 3, 5, 6, 7, 8, H O C 1, 2, 3, 4, P H 5, 4, 3, 8. Oh. You see that they have the same molecular formula. Why is it faster than the structure? So one the arable formula and the keto formula, that is aldehydes and ketone are functional group isomers. You can take the case of an ester and a carboxylic acid. So let's take the case of an ester. Now CH2 is CH2. Or let me give the formula first. Let me give the formula. So give me the formula you have C4 H CH2 is CH2 CH2 COH 8 3 plus 7 8 5 6 7 8. Okay, good. That was 5 7 8. Beautiful. This is a carboxylic formula. The formula is C4HAO2. Beautiful. So that is the carboxylic formula. We can have now the ester formula. The ester formula would have CHC, CHG, COO, CHT. Carboxylic formula, ester formula. Anyway. And actually, the isomers, if you check critically, you see that the isomers, they have the same number of carbon, the same number of hydrogen, the same number of oxygen. So, we're not going to see optical isomerism. So, optical isomerism, all what we have been seeing since the beginning was structural isomerism. So, optical isomerism. So, Stereoisomerism. Stereoisomerism. I give that stereoisomerism, there are two of them. There is optical and there is geometric isomerism. So we're going to start with optical isomerism. So what do our optics? We value refer to a mirror. So optical isomerism, there is a condition. Optical isomerism, normal. Optical isomerism, there should be a condition. The presence of what we call in chemistry a chiral carbon. Chiral carbon. What's the chiral carbon? The chiral carbon is a carbon that is surrounded by 4 different functional bits. So a chiral carbon, let me put an example in the chiral carbon. C, methyl, OH, the arrow, Cl. In this case, you see that the carbon is chiral. Chiral or an asymmetric carbon. So whenever we have a chiral carbon, there will be the existence of what? Of two main enantiomers. The enantiomers are non-superimposable. So the enantiomers, one you have the level enantiomer and the destro enantiomer. So let's consider the molecule C4H8O. We have the molecule C4H10O. The molecule C4H10O. Okay, I rearrange the molecule CH3, CH2, COH, C4, hydrogen. This compound, this ZDL are expanded. The what you rearrange? The compound contains a chiral carbon. Here's the chiral carbon. I'm going to condense the compound in C. Condensing the compound, I'm going to now C OH CH2 H C2 H1. So here's an ethyl group, hydrogen, methyl group, OH group. So this carbon is essentially chiral. It's an asymmetric carbon. So I'm going to draw the isomers on the board. Don't forget there are two isomers I'm going to draw. So there are two isomers I'm doing. I have this isomer here. I put this to represent behind the plane C2 H5 in front of a plane H in the plane OH. I shoot a mirror. Here there is CH3. When you put the mirror, the image becomes laterally inverted. The lens becomes the guy becomes melt. So this isomer is what we call the positive isomer. So that side is a negative isomer. So when you put the mirror, the compound is laterally inverted. So this one goes behind. This one, here we're running C8B. Then I have a C2, A5, H, OH. The image become laterally inverted. So at the advanced level, in front of the plane, in the plane, inside the plane, in most cases not given. But to be more matured, you have to indicate in the plane, in front of the plane, and nothing else. Then in the university, you guys will see what we call the absolute configuration. It's a configuration array or S because we have two main configuration we can use it. Either as arrow or S. The one where you put a mirror, there's an inversion of configuration. That is why the enantiomers are non-superimposable. So the molecule of butyl 2-ol is not the molecule that comes from the whole geometric optical isomerism. One color molecule. So let me give you the color molecule. So let's take a case of C H2 CH LH2 COH. The amino acid, two amino propanoic acids. Okay, so let them draw the isomers. Line C, I think behind the plane. Behind the plane, circle. In front of the plane, LH2. In the plane, hydrogen. Yeah, put COOH. So here I usually like quoting university because this is just the introduction to organic chemistry. University, you people will see what we call the Cam Ingol Pelop rule. Cam Ingol Pelop. The Cam Ingol Pelop rule there is used to see how you can order this substituent in order to give the absolute configuration. Why are we studying this enantiomers? You as organic chemists, you can synthesize a molecule. One of the isomers is actually a it cures. The other isomer is a toxin, so it's toxic, it can kill. The real problem is how will you know which isomer is useful, the other isomer is not useful. Like the case of an orange, there are two varieties of oranges. So what give the characteristics a difference in smell is due to the existence of isomers. So one isomer can give a sweet fruity smell. The other one can give a pungent smell. So that is why we study isomerism. So let's see how we can draw an isomer of this molecule. You put a mirror, the image becomes nothing and image. So the length becomes bright, the height becomes the length. Yeah, have that S2 hat. Okay, let's go send on to geometric isomerism. So geometric isomerism is quite different from optical isomerism. For geometric isomerism, we need to have two main conditions: the presence of the double bond and also the presence of symmetry. So we want to geometric isomerism. For geometric isomerism, we need to have a double bond and a symmetry. For geometric isomerism exists due to the inability of the carbon carrying the double bond to rotate freely in space. Due to this inability, they give rise to two main structures, the E for hydrogen and Z for zooxanthellae. In this case, let's take the case of butene dioic acids. Butene dioic acids. Why in biology people call malic acids or oxaloacetates. So you know C4 plants, the first product form is oxaloacetate. Now that's why we call a 4-carbon compound. That's why we call it a C3 compound. A C4 compound. So in this case, you have this compound reverse. That's you. So I have a compound with 4 carbons. So you have 4 carbons. 1, 2, 3, 4. Top. Then I want to draw the isomer. I can have two main isomers here. The cis isomer and the trans isomer. Cis means together, trans means opposite. So let me draw you the isomers. H, H, O, O, H, O, H, C, Ergon, O, O, H, C, O, O, H. Cis mates together can case opposites. On the above the answer main isomers A and B. Which one is cis, which one is trans? It's very simple to identify which one is cis, first of all. Cis means the substituent are found together. So in this case, we have the cis isomer, you have trans isomer. So we can map all the molecules, like in the case of 1, 2, like a scene. So the model is C, Cl, Cl, H, what is C, Cl, Cl, H. This means together, so you map cis, double amps. The cis and the trans isomer. So that's all about geometric isomerism.